All right, let's talk about AI and software engineering, but we're going to skip past the usual hype about code completion. Instead, we're going to put on our architect hats and really lay out a strategic roadmap. We're talking about how we get from AI as a simple tool to full-on system automation, where AI becomes a genuine member of the engineering team. Okay, so this slide right here, this really sets the stage for our entire conversation. For the past couple of years, we've all been living on the left side of this chart. AI as a code generator. Think Copilot, giving you a little autocomplete for one function. And hey, it's handy, but it's small scale. Where we're going and what we're focused on today is everything on the right, system automation. We're talking about AI agents that work at the repository level, agents that can pull off complete refactors and actually understand complex, interconnected logic. This is the jump from just writing code snippets to actually architecting systems. So here's the plan for our briefing. First, we'll look at the new AI landscape that goes way beyond just code completion. Then, we'll get real about the bottlenecks. What's actually stopping us from automating everything right now? After that, we'll lay out a practical roadmap for getting there. We're also going to zero in on a huge potential win, using AI to tackle our technical debt. And finally, we'll look at the big prize, getting AI to help us with long horizon planning. All right, first up, let's expand our thinking here. The world of AI and software engineering is just exploding. It's not just about writing code from a prompt anymore. Not even close. I mean, just look at this. The AI toolkit today is touching pretty much every single part of the development lifecycle. We're seeing tools that can refactor your spaghetti code, automatically migrate an entire code base, like, say, from Python 2 to 3, and even generate really sophisticated software tests. It's even pushing into these incredibly complex areas like program repair and formal verification. This means AI is becoming a partner from the very beginning of a project all the way through its long-term maintenance. Now, this is really cool because it gives us an architect's way of thinking about and evaluating all these new tools. You can basically measure any AI task on 3 different scales. First, you've got scope. Is this thing just changing one little function, or is it touching the entire project? Second, logical complexity. Is it doing something simple, like calling an API, or is it trying to do something crazy, like design a new algorithm? And third, human intervention. Are we just using AI as a tool we control, or is it acting more like an autonomous agent, making its own choices? As architects, the goal is always pushing toward the right side of these examples: large scope, high complexity, and minimal human oversight. So if these tools are getting so powerful, what's holding us back? Well, that brings us to the real-world bottlenecks. These are the things that tend to completely break when we try to apply these AIs to our massive, messy real-world systems. And this is the million-dollar question, right? If an AI can write a perfect little function, why can't it just, write the whole application for us? Well, the answer is that the leap in complexity from a single file to an entire system is just astronomically huge. The first really big roadblock is what we call long horizon code planning. This is the absolute essence of software architecture. It's not just about writing code that works right now. It's about choosing abstractions that will still make sense a year from now and structuring the whole system so it can actually evolve without falling apart. A great human example of this is the React Fiber refactor. That was a massive, multi-year project to completely rewrite React's core, all while keeping it backward compatible. That kind of foresight is just way beyond what any AI can do today. The second bottleneck, and honestly, this might be the biggest one, is semantic understanding. An AI can understand the syntax of a function, what the code does perfectly, but does it understand why that function exists in the first place? Does it get the unwritten rules, the business logic, the implicit conventions of that specific codebase? Without that deeper layer of meaning, automation isn't just ineffective, it's downright dangerous. And this table just perfectly shows how those big, abstract challenges turn into our day-to-day headaches. When an AI struggles with a large scope, you see it get confused and lose track of dependencies between files. When it can't use tools well, it's like having a junior dev who refuses to use a debugger. And of course, when it lacks that semantic understanding, you get the absolute nightmare scenario. The AI helpfully refactors a module, and in the process, completely shatters the critical business logic it was supposed to protect. Okay, enough with the problems. We've defined the challenges. So now let's talk solutions. How do we actually build a road to get to true system automation? Well, the research points to a pretty clear and strategic path forward. It really boils down to this 3-part strategy. First, we have to curate way better data. Second, we need to come up with much smarter training methods. And third, we've got to build deeply integrated tooling. Let's dig into each of these. So when we say better data, we don't just mean more code. We mean richer code. We need to feed the AI training data that's been augmented with info from static analysis, from runtime performance profiles, and, this part is absolutely key, from the fine-grained signals of how a human developer actually works. We're talking about capturing every edit, every debugging session, every code review. We have to teach the AI the process of building software, not just the final result. Next up is smarter training. And the big idea here is something called reinforcement learning from verifiable rewards, or RLVR. So instead of just showing an AI a bunch of static code, we build a gym for it, a realistic, executable environment where it can actually try to solve real engineering problems, like fixing a bug. The AI only gets a reward when the code it rates actually compiles and passes the real test suite. It's learning by doing, by failing, and by trying again, just like a human engineer does. Okay, so let's take this roadmap and aim it at one of the biggest, most expensive problems in our entire industry, our mountains and mountains of technical debt. This is just a perfect use case for system-level AI. And if you want to understand the scale of this problem, just chew on this number for a second. Over 220 billion lines of COBOL are still out there running critical systems. Just think about that. Migrating or even safely maintaining that code is a monumental task, and it's perfectly suited for automation if we can just get it right. So, here's the AI-powered 1-2 punch to deal with all that legacy code. Step 1, we unleash an AI to generate a massive, really comprehensive suite of tests. It's going to find bugs that have been hiding in that code for decades. But step 2 is where it gets even more powerful. We use AI-assisted formal verification to mathematically prove that certain properties, like memory safety, are guaranteed. This doesn't just find bugs, it eliminates entire categories of bugs permanently. And that brings us right back around to the grand challenge: getting AI to actually help us with long horizon planning. Can an AI learn to think like an architect? Can it help us make those highest level decisions about system design? For an AI to ever be trusted with this stuff, it has to learn to value the things an architect values. It can't just spit out code that works. It has to design good, lasting abstractions. It needs to care about modularity and code quality, not just cram everything into one giant function. And maybe most importantly, it has to learn to respect the unwritten rules and conventions of a codebase. This is what's essential for those really hairy migrations, like moving a huge system from Scala 2 to 3, where understanding the spirit of the code is just as important as the syntax. At the end of the day, it all comes down to this. Through all the automated refactoring, all the migrations, all the optimizations, the core purpose of the system, its semantic meaning, has to stay intact. The AI can re-architect the house, but it can't forget that it's supposed to be a home. Preserving that meaning is the hardest and, without a doubt, the most important part of this whole journey. Which, of course, leaves us with this final big question. As these AI agents get more and more capable, what does our role look like? Well, the answer is probably not a human or an AI. It's almost certainly a hybrid team. A team where human architects set the vision and the strategy, and AI agents execute these incredibly complex repository-wide changes with a speed and a precision we can't even imagine. The future isn't about being replaced. It's about a fundamental evolution in what it even means to build software.